Levi, John, do you see the content? John is seeing.
No.
No? Okay, we will project it. John, who has a 30th birthday? Whom should we congratulate? You have a balloons with two numbers. You? Okay, let's tell happy birthday to John.
Happy birthday.
Happy birthday, John.
Happy birthday.
Is it today?
Today?
Today, exactly today.
Really today?
Oh, we need them to sing a song.
Not today? Today?
Yes, today, no to singing.
Okay, yes. Yeah, happy birthday. Have a health, success, inspiration.
Thank you.
Okay. Send SMS to one of us if we do not hear you, because right now we are going to put slides on main screen and then it will disable voice line.
Is there only John?
No, John and Levi. Okay, well, thanks for coming and investing your time into these meetings. Today there will be research presentation by Aaron, and he will tell about his research with a strategic overview and assembly of the pieces together. Okay, floor is yours, and please check if it is the right version of the slides.
Probably be close enough. So yeah, this is presentation for today's group meeting. I don't know, what is today even?
10.
10? Yeah. I just knew it was after the 4th.
So you were not sure about today's date?
Yeah, I think I started making it like a week ago, and I had no idea what today's date would have been.
Does remote advance work?
This time,
remote. Okay.
It's a great connection with John.
Maybe it's on occasion of his birthday.
John, is he hearing us?
He is hearing us, but we don't hear him. But he can just show by signs.
We have very great connection today with you. Usually you are not as well seen as today. I don't know, maybe you got a new internet or something. New package. Higher speed or something.
So, and just before beginning, just a little bit of background. So, like over the past, I don't know, half year or so, I presented a couple of times on 2 projects I've been working on, a doped quantum dot and an intrinsic quantum dot, and most of that has been submitted to journal PChemC already. And then I guess Dimitri's plan was to take some of the leftover remaining parts for the intrinsic dot and then formulate that as a letter for the physical chemistry. Physical chemistry.
This is your goal for your publication, or it was already published there?
Goal. So this is what this is intended for.
And only to the letters?
Yes.
What if it's not accepted? Plan B?
Plan B and their loss, I guess. I don't know.
Okay. But yeah, okay. It's a goal.
Yeah, so it's like, I don't know. I've seen the journal physical chemistry letters before, but I had no idea like what's different about it compared to other journals. And I guess I just found this on the website. You can kind of read the journal scope yourself if you can read it. But basically, they have different types. You can have like people giving their perspectives, their own ideas on materials. I have original research articles, and I guess that's probably what mine will end up being focused more on, is the original aspect instead of providing our 2 cents on, I don't know, the properties beyond.
But your goal is to have a short paper, right? So
Sure.
because lattice means it has to be short. It's like a short report.
Well, that's probably what they enjoy, but I've seen some letters that just kind of go on and on and on, so.
But it depends on the editor, but usually the words lattice in a title of the journal kind of is
Yeah.
a limit in number of pages. Usually they should have a limit in number of pages.
Yeah, so I think
Or
they
number
kind
of
of,
figures, and some journals are more restrict, some journals less restrict.
yeah, they don't explicitly say, but they say that the point of the journals is for rapid publication, so if you have something important to say, to get it out quick, so the
Of
idea
course,
was,
everything we do is important.
yeah. So, yeah, I guess that's just kind of going into what to expect, or how to try to formulate, or try to organize the data that I presented. And
But maybe there are some other ideas, like let's say maybe alternatives, not exactly plan B means low level journals, but alternatives to these journals, maybe some people know. What would you kind of recommend? What other journals, maybe not ACS journals, which might be kind of pretty much comparable to this one?
Anything that
No
has. I have an idea.
Oh, okay.
Anything that has word nano in the name of the journal.
nano letters.
It's more competitive. This
Nano letters is much harder to publish.
Than this one.
Yeah.
I think
There's
this one's-
also ACS
energy,
energy letters.
were,
I think Journal of Energy Letters. are
and they
probably
specifically like papers and perovskites.
Yeah, I've
definitely, it's probably even more focused journal, so you probably have a better chance. And also impact factor is very high, probably even higher than for this one, but not very much more higher, right?
Yeah, I think they're all around like plus or minus 10 in that range. Some are like 13, some
Plus or
are like
minus 10?
No,
or
a little
10
bit-
plus or minus.
Oh, okay.
9, 8, I would say, yeah. So I think JAX has now citations something around 14.7. This guy's low.
Yeah, relatively. Well, yeah, but it's higher than Journal of Chemistry C. Which
There's
is
also
what-
Materials Chemistry journal, also ACS journal, materials. I think it's either Materials Chemistry with a focus on the materials. It's also having a impact factor around 9, but there is no restriction on a size because there's no word letter, so it's more like a full style paper. So if it's really long, you probably have to choose something different. There is also applied, there are several new journals which kind of a series, so it's apply energy materials, not energy letters, but energy material, applied energy material, ACS applied energy materials, ACS applied nanomaterials,
Materials, yeah. Okay, yeah.
and ACS applied interfaces, how's it called, surfaces, interfaces.
Yeah, those ones seems more like, well, the articles I've seen on that, they seem more experimental based.
Right, but-
Computational, but maybe.
But no, there is not, like, again, so if you read carefully the scope of journals, so they usually don't just request experimental papers, right? So, okay, if you want to try something beyond ACS, I would say there would be nanoscale journal. This is Royal Society journal, which is also high impact journal. Well, it's less than this one's, but comparable. There's journals like Small. It's also European journal.
Small?
Small.
Never seen that one.
Well, because it's a European journal. They still have a very high, like if you Google and check impact factors. But I mean, I like the idea that you start thinking about the paper, you start thinking about paper exactly to the journal where you want to publish, but I would say you probably can then really check what other possibilities are there, rather than just focus on this journal, which is very good journal of physical chemistry letters, but I said like there are really many alternatives which probably very, very comparable to this one. Beyond there are several in ACS journal series, and there is definitely several beyond ACS European journals.
That's true. I think one reason that we wanted to pick this one is it seems like, well, whenever I look at journals from this, they're disseminating information, but it's also like kind of advertising like the specific instrumentations or whatever specialty they have. So that could be another reason that we do. Let's just showing the capabilities that we have as a group and what we can calculate. Because I don't know, I usually see more. I see like a lot of letters like floating around, so it's easier to
It's like
get
nothing
into.
wrong with your choice. I'm just saying that there are much more than just this. And if you're choosing something, I would say like it's probably should have some kind of reasoning that you really know, not only about this journal but other possibilities as well. Right?
So
Based on T-shirt, labeling Aaron is very serious.
United we fight?
Yeah.
I think it's a cancer shirt. That's what this little.
Oh, I thought it's a gam.
Oh, okay.
Well, there's the gamma too, probably. I think it's supposed to be a ribbon. I don't know, it's not my shirt. I think I stole it from one of my friends just because it fit me. But anyway, so yeah, that's philosophy behind Journal of Physical Chemistry letters. And so I was thinking along the lines of like kind of advertising or grouping the specific skills that we have as a group together. So some of the main things that we can look at is, I got flipped a little bit, but ground state electronic structure of materials. We can compute absorption spectra of materials pretty available readily and have capabilities that other groups don't have. A wide variety of topics I call structure to property relations. So I mean, you could literally put any sort of category into structure to property relations, but when I was thinking about this, I was thinking about effect of ligand choices on the quantum dot. So either full passivation versus under passivation, its effect on electronic structure, and then alternative ligands that people use try to passivate these to increase their quantum yields. And we also do, well, the most competitive aspect of our research that we have is excited state dynamics of materials in general. So hot carrier cooling and computing photoluminescence properties of materials. And so how do these all kind of connect together? So the ground state electronic structure serves a basis for absorption and spectra calculations, because with the ground state electronic structure you define electronic states, and then determining on orbital overlaps or atomic orbitals that overlap with each other, you can those will determine your absorption spectra for dipole out transitions anyway. And then your ground state electronic structure corresponds to your excited state dynamics, because we use ground state structure as the basis for excited state. So that's how those kind of correlate together. And on the right hand side, you can go back from structure property relations to kind of connect all these. So the types of ligands that you have and the type of passivation is going to affect ground state electronic structure.
So here you are not including the part on your doping for manganese.
Right, this is just intrinsic.
Okay.
Because, well, mostly because they haven't figured out the.
So your main focus is on ligands on the surface.
So yeah, basically interaction with ligands with the perovskite quantum dot, and then just general properties of.
So title, probably. The first thing which you probably can think about for your paper is a title.
Oh well.
No?
I guess I'm going from the opposite view, I guess. So I think Dmitry gave some advice to Sergei Chetriak about different types of research approaches you can have. You can either have like high precision, one aim, one bullet, you have one shot, or you can either have like buckshot and try to spray everywhere, and then you have better chances of getting success. So a lot of these is like just exploring different paths and seeing what's worth going down eventually. So I don't have a specific title.
You thinking that you probably have to split this and make 2 papers instead of 1 from this material? So what? From this information?
So I'm just kind of outlining what I have already, and then deciding what's worth exploring, what's interesting to explore, that could give novel insights to these perovskite quantum dots.
So, after overview of available things, can you make reverse engineering and tell which experimental challenge is targeted to be addressed? by this research.
You're an expert in the field right now, right? If you're in a stage of writing a paper, you definitely know what's going on in the field.
What is not known in the field, and
So you
what
can
can be
really
addressed?
say what exactly of your parts are really the most challenging, the most important, the most interesting to not to you or to me, but really to the community who are working on a perovskites.
Yeah, well, I guess from that sense it would be the excited state. Wrong button. Excited state properties, which
But what exactly is the challenge there? People can measure excited state properties. What's the problem?
origin,
Huh?
like origin of where these properties arise from.
Uh-huh.
So the popular name you'll see thrown around is Rashba effect, and then people usually use that to explain why either a non-radiative relaxation is suppressed in materials, or why you get
So
flipping of your.
I will rephrase it again. So you're saying that the main challenge in the field right now, especially if we're focusing on these perovskites quantum dots, right? Not just perovskites in general, is really to make them luminescent. And they're still a sparse, or how say, maybe not sparse, but maybe there are a lot of maybe research focused on these questions, but they are not given the very clear ideas how to control the emission of these materials. Like different groups probably report very different values for quantum yield of these materials, right? And in some cases they're really very emissive at this range of energies, in the other cases they're not emissive, or what? This is a challenge?
So the challenge is.
Or it's not a challenge to make these guys to be really bright, nice.
Yeah, they're like
emitting
as soon as you
materials.
make them, they're pretty much bright. Even if they degrade, they still have luminescent properties of like 50% quantum yield. So
it's not a problem to make them bright.
it's understanding why they're bright.
Okay,
And
then what is the challenge? I didn't get it yet. So people can make it, people can synthesize the materials, and without really a big efforts, if they synthesize this quantum dots, they already see pretty high quantum yields. 50% is really very high quantum yields.
That's even after they degrade. So if you make them fresh, they're
Right.
brighter.
So looks like, yeah, you just synthesize and they're bright right away. Then what is really still unclear there
So
in terms of this dynamics, for the excited dynamics?
I guess a couple of things are people. I guess I didn't put it into the presentation, but I was just looking at some literature, or refreshing on some of the literature, and like bulk perovskites, they have very slow hot carrier cooling, which is useful for like solar cells because you want slow recombinations. But in quantum dots, they see like sub-picosecond around like 200, 300 picosecond non-radiative relaxation.
Non-radiative
Or
relaxation.
not
Oh.
hot carrier cooling.
Relaxation rates, okay.
Relaxation rates, and then people either trying to understand whether it's Auger effects or whether it's phonon processes or
The mechanism of
right
this quick
or due
relaxation
to
rates.
ligands. There's usually the three that are flown or suspected for cooling rates. And
So what affects this effects in higher extent? Choice of ligands or quantum confinement?
it's a good question.
Would it be a challenge?
Well, again, what do you think? If you just look on a model of the quantum confinement, let's say you just really make your perovskite start with a bulk, right, where the relaxation are very, very slow, and then you go smaller, smaller, smaller to really nanometer sizes as you're working, right? So just using the knowledge of quantum mechanics, what do you think? What would be the effect of this confinement on relaxation rates, intuitively, based on a kind of general knowledge of quantum mechanics?
You just squeeze your charges together so they're more likely to scatter off each other or interact, or just, I guess, non-radiative relaxation would increase.
But we're talking about interband relaxation, what you call hot cooling, hot carrier cooling or something like this, right? What you're saying is right, but how this really deals with your relaxation? Okay, what happens with electronic levels when you go to the confined systems?
Oh, they become more sparse or
And?
further apart.
Okay,
And
more discrete?
yeah,
So?
So you have more bands, or
So,
higher energy.
how this affects the interaction with phonons or with vibrations?
We need more of them, or it's the probability of a phonon with a certain energy to jump the gap is less, so it takes
Decreasing.
longer.
So it should be slow actually, right? So intuitively the confinement should lead to even slow relaxation rates comparing to the bulk materials, because you really increase in a mismatch between phonon energies, which is usually small for the inorganic type of materials, right? They are low frequency phonons or low frequency vibrations. Comparing to the splitting between your electronic levels, which is definitely growing and getting, you can really estimate it based on your models to see what exactly is the splitting between your levels.
Yeah,
Right?
near the band edges, it's like
And it's exactly the
0.2,
same story for
0.3.
the semiconducting quantum dots, right? So again, people were expecting that relaxation rate should be decreasing, that the relaxation should be slow than in bulk because of this confinement effect, because you having a mismatch between energy of much larger mismatch between energy of phonons and the splitting between electronic levels when you go to the quantum dots comparing to the bulk materials. But experimentally, they don't see it. Actually, they see not faster. In case of semiconducting quantum dots, it's comparable. The rates are not really changed in bulk versus quantum dots. And they become a little bit quicker. It's also not sub-picoseconds, but picoseconds. So it's picosecond rate for the bulk material, picosecond rate for the quantum dots, like cat selenide, cat telluride, lead selenide, gallium arsenide, and so on. Silicon quantum dots as well. So they all have pretty much kind of picosecond rate relaxation, which is very similar to what is seen in the bulk materials, which contradicts to these simple ideas of the confinement change in confinement effect on the energy levels, right? So, and again, there was a discussion on this question for quantum dots. Now you kind of also see the contradiction, probably even more significantly seen in these systems in perovskites, right? So looks again, so that confinement should lead to completely opposite trends rather than what is seen experimentally. So that's really becoming, like, if you put it in this language, right? So you probably can see that then this challenge becomes really very interesting. Like, oh, really, why? Why it goes against the very simple idea of this particle in the box or whatever kind of very simple model, which looks like you can easily apply to this one, and clearly the levels are becoming sparser, right? Becoming more discrete. Then there definitely should be some other mechanisms. And probably this would be your focus of your paper, really kind of, and again, what are the mechanisms? Surface, ligands on the surface, right? This type of things. They probably now really having probably the most significant impact comparing just to the confinement. And they provide some additional channels for this quick relaxation.
Yeah, they're
somehow.
actually, I was going to touch
But what
on that a
exactly,
little.
like how this works, what exactly, like just to say that, oh, we are guessing that this would be probably the reason, right? This is good that we have some ideas, but we need really to prove it to understand how exactly it works, what exactly is the physics behind it, or chemistry behind it. And I guess you can easily wrap these kind of ideas into your challenge introduction part of your paper, really focusing on trying to answer the question, what exactly is the mechanism which governing this fast relaxation, which kind of goes against the confinement idea, or the confinement effect.
Yeah, I guess something
And definitely this probably would be the role of ligands, and you can really then move to the more detailed explanation and focus on ligands.
Yeah, I've thought of it, but I think it was one of our group meeting discussions. We talked about trying to get spectral densities from our autocorrelation functions. I think, didn't you say something about we don't have the resolution? Or it's like we run too long at time steps, so we don't get as good.
No. Well, there are different things. There are technical aspects and there is a strategic planning. So we can be aware of mechanisms and think about them even without doing experiments or calculations. Right now the question is just how to navigate in the space of this knowledge area. we cannot address all questions by making experiment or running simulation, but we can overview the field and pick up the spot where we can contribute.
Okay.
So your central point is really showing how these relaxation rates are affected by ligands and by size. No, I don't think you change in size of your quantum dot. Just by ligands, right?
Yeah, for this model. We are working on bigger dots, but
this is definitely looks like that this is your central point. And again, for this central point, in your introduction part, you can really make a kind of very clear statement of a challenge. Why the question which you're addressing, how the ligands affect the relaxation, why this question is really important, interesting, and needed to someone, right? So, and this kind of wraps up the whole story. And then you can go into the details. You start with your ground state, with your some other features and so on, right?
Yeah, that makes sense.
But your core part would be really this one, which means it's definitely probably will be at the end of your paper, as the very last chapter of your paper probably, or last part of your paper, right? And before you start with the ground state properties and so on, and really kind of end up with this final results for the relaxation, and finally answer the question why the relaxation is quick. Like what exactly is the role of this or that ligands play, right? Because I guess it's probably because of ligands, that's why it's quick.
Yeah, because I think, well, I didn't get there yet, but.
Oh, you don't know the answer yet?
No, I was going to say it's the rates we computed, they're a little bit quicker than what's seen in experiment. And I was going to say that's probably.
If you think about qualitative approach.
Right, I was going to say that's probably going to
quantity.
Our surface, it's like, well, our quantum dot is basically all surface, so it's mostly ligands impacting.
But in experiments, they really work with exactly the same size systems? Or the quantum dots are bigger?
They're bigger, like, ours is like 1.5.
So then why you expect to have exactly the same numbers? Of course, the size will be affecting these values, but qualitatively at least, right? Just thinking what exactly the origin of, what exactly contributes to this relaxation, what is the channel?
Right, that's why I was saying that's why ours are probably a little bit quicker. It's because we have more ligand to
because you have much more surface.
So
okay.
that's so you have more driving force from the surface compared to if you have a 10 nanometer dot, you're gonna have less density.
Yeah. So you already explains why it's quicker, but it's not really destroys your main ideas for this paper, main points which you want to address in this paper.
Mm-hmm. Okay.
Maybe, I don't know.
So we are done with 3 slides out of 33, right?
33?
A lot of them are transitions. So yeah, just how structure property relations can relate to other aspects of the research. So how ligands can affect excited state dynamics, for example. So first, I guess we'll start talking about ground state electronic structure of these quantum dots. So I figured since a lot of these letters, they kind of take like some sort of a little bit of perspective or historical notes. So the first place to start for quantum dots would be with papers by Bruss when they're originally kind of discovering quantum dots or quantum confinement systems. So this is like one of, it wasn't his first paper, but it's, I don't know, it was the best one I found that kind of gives an intuitive introduction to the approximations they use to describe the electronic structure in quantum dots. And so when they're first looking at these systems, they're seeing that the smaller they make the cluster, the more blue shifted that you see the absorption spectra. So this is represents the bulk band gap for, what are you looking at? Zinc, selenide, some sort of system. So this would be like a bulk material. And then you make a smaller, medium-sized cluster, they called it. You see absorption increase and then blue shift, and then even increase more in blue shift. And so the theory that I used to try to describe this is, I kind of summarize it in one slide here. So he does a better job explaining it in the paper than I can, but basically, if you do any sort of solid state physics, you see any of your wave functions, they have basically two parts. You have like a plane wave envelope, which is this green, these green lines here, and then you also have like a periodic part that goes through like your crystal structure. So if you imagine each of these blue blocks is like a crystal lattice periodically, so this one is like a bulk material, so it just keeps going on forever. So you have your periodic function keeps going, and you have nodes where the wave function goes to 0. Then you have, for your lowest energy state anyway, a very broad envelope function. And then he realized that if you take like a cluster, so if you just have like a finite system, that your envelope function basically just turns into your particle in a box solutions. So this phase factor here basically turns into a sine wave. And then you do your normal particle in a box solutions that a lot of us have probably done a couple of times. And you arrive at that the energy of your state is basically what its ground state would be, plus some confinement effects where this is like what you normally see from a particle in a box solution, except he did it for spherical, so instead of a length, edge length, he used R.
Can I add something?
Mm-hmm.
So your orange line is expected to show the
Is it kind of blocks function or something like that?
Mm-hmm. Yeah.
to be the same on each atom, right?
Is it orange line is the same in the cluster and the
So it just the
So should the top
present image of the orange line could be a little misleading because it is slightly different.
Yeah, it was just easier to draw it as period, but the tops of each wave should approach the top of the envelope function.
So it is atomic functions.
Yes, so it's like your molecular orbitals.
oh yeah.
So that's what the orange lines represent. So it's like at each crystal lattice you have your atoms, and then you get your molecular orbitals from there. And then, yeah, so this energy is just like the energy of either your electron at the top of the conduction band or your hole at the top of the valence band. And you get your band gap energy, which is...
If it will be whole, then minus instead of plus, right?
Yes. And from those you can get an effective band gap, or your new band gap, or your confined system. So it's the band gap of the original plus your essentially confinement terms plus some higher order terms that people usually neglect when they model these systems. And so, just as a little exercise, we figured we'd try a good idea to see if we could model the ground state structure of the perovskite quantum dots using just the simple part or effective mass approximation. That's what this general theory is called. That was developed by Bruss back in the 80s. And probably other people too. So this slide is basically just comparing the density of states for just some simple modeling using basically using the envelope functions. So these are basically particle in a box.
It looks like you comparing DFT dose versus your particle in the box
Yes.
dose, right?
So
But you have only one line on your figure. What is your particle in the box dose?
So this is the particle in the box dose. This one got
Oh, I see. So it's different figures. Whoa.
Yeah, it got screwed
And
up.
you.
Whoa, yeah.
Okay, so it's actually you're showing them on different figures,
Yes.
and actually your x and y is also different now. Okay, it's better. Why not to show them together on one plot for easy comparison?
I didn't get that far yet.
Okay.
But yeah, that looks better.
And also, when you're calculating your particle in the box, it's actually called effective mass approximation
Yes.
approach. So you have this m star parameter here,
Yes.
right? So where you getting this parameter and what is the meaning? I maybe missed it. Did he discuss it already?
I guess they were part of the last slide. I didn't go into them into detail. So basically,
I mean, I can wait till your last slide. I just can hold my question.
or I mean, last slide is in my
meaning
previous slide. But basically, so the effective mass basically comes from like the curvature of the conduction band. Like that's just the technical way about it. But basically, you can relate the band structure to an effective mass.
But have you done it by yourself? So you
No,
took it from your
these-
DFT calculations,
these
or where
were-
did you get it?
Like these are calculated from literature. The people,
Calculated or from experimental data? Because people can measure this from
right.
effective mass.
I think
Effective mass can be measured.
I think I pulled it from a calculated one, but it,
For the bulk materials. For the bulk perovskites.
yeah, it must have been. I can't remember the technical details, but I just pulled it from a calculation that somebody did in another paper. Just for
For exactly the same system, right?
Yeah, same
chemical,
atomic composition.
chemical composition.
I think.
But recheck. I think it's probably based on the bulk materials.
I think
on the
that
bulk dose.
if electron effective mass, I think, was a little bigger than one, I think the whole was a little less than one, which, yeah, I think that checks out. Because usually if you have a higher effective mass, you have lower density of states. So, yeah, that must have been how it's plotted, because that's how it is here.
Higher.
Or is it the other way around? So if that's a bigger
Okay,
than one.
if you, there are two things which again might be a little bit confusing, and this was also very related to Fatima's discussion. So we talk about density of state, or we talk about band structure, and you see the difference, do you? If people say band structure, what is it?
Oh, that's
What you will show,
dispersion,
yeah, what you will be your x and y on your figure.
energy and momentum.
K vector, yes. And DOS is just the number of states, kind of a, how to say, distribution plot, right? Number of states versus the energy. So then if you go to the band structure, and probably you need to do, is it possible to do some drawing? You were doing it last time, right? So, and also, I think John was also showing some kind of pictures like this in his presentation. So how you think this, like, we're thinking about parabolic structure for the band structure, right? How your energy changes with K. And this parabolic structure would be going down for the holes, like your parabols will be pushed down, right? And parabols will be pushed up for the electrons, right? So you will have something like this picture.
Right.
And then the question is, if you call heavy hole or light hole, how this will be changing your, kind of just schematically, how this will change your band structure. I guess it's better if you just draw it.
Yes.
Project their own.
He will show just one.
Okay.
Something like that, isn't it? That's
And
the
which one is which one? Your dashed lines
dash?
would be,
That'd be the light hole? No.
well, you said it's proportional to the curvature. The heavier, the more
Percent
curved
derivative
it is.
If what the
Am I right?
constant in front is your value.
So I guess light hole means it would be less curved. Or like,
You can look at from here, like if m is
Large number in the denominator means small total value. So the flat line is heavy particle and steep line is light particle.
So you give it a little bit of momentum, its energy should change more if it's lighter.
and now if you look on energy, like now you kind of going from this picture to your dose, means you kind of adding all your K values to one dose. Which dose will be having more peaks at the given range of energies? Those for your, how to say, less curved guys or for more curved guys?
You mean at the edges? Is that what you're saying?
Well, to get your dose, like getting from the band structure to the dose, you just take in your energies and kind of sum over K. Adding your energies at each K.
I guess this is just for a single gamma, or single.
I understand, but again, if it would be not a if it would be bulk material, and you're trying to really kind of talk in a language of bulk material with this one, so if it's a bulk material, right? So then the dose, how would be looking the dose for these guys in case of very curved and less curved particles? Well, just look how many, choose your energy range, right? And think how many of them will contribute for the less curved and more curved.
Well, for your LiPo, you'd have larger spacing between states.
Yes, and heavier will
Be less.
So it is denser.
Denser, right? So the heavier the mass of your carrier, then your dose will have kind of a higher peak because your states will be more dense. And again, I don't know, for me it's very easy to see from this graph because you really kind of choose. Let me take it. Maybe the pen. So, like this dashed area, this is kind of your density of states at this small delta E, right?
Mm-hmm.
And clearly this will be much more in an uncurved guy comparing to the curved guy, right?
Right.
So then again, going back, the more denser, the heavier the carrier would be, right?
It's a bigger number.
Because heavier means it's less curved.
Yes.
Yeah.
I'm just
Must be
wondering
the other
that
way around.
okay, mass is related to the curvature of a band, but density of a state is a number of band in a certain
But this is
energy level.
again, is it proportional or reverse proportional in the formula for the mass and curvature?
The larger the mass, the
Curvier.
flatter.
Or the flatter?
Yes.
Yeah, but that will give us information about the shape of a certain
But
band.
this is exactly what I was
Yeah.
giving you in this figure.
Yeah, but
So we have very different shapes here,
Mhm.
right? And again, the curved, which mass would be smaller, the dashed or the solid line?
yeah, I got this point, but I'm just wondering how is it related with the density of the state? Because
That's
density
exactly
of
the
the state
answer for
number
your
of-
question. Now, density of states will correspond to all k values, right? Like in this crossed area. So because
oh, okay.
you're choosing a very small delta E, right? So it means all energies from this K, which I crossed, which I kind of, put like a crossed area, right?
Oh, okay.
Contribute. And definitely area under the curved guy is smaller comparing to the uncurved, to the flatter guy. So which actually means that your density of state will be higher for uncurved, for heavier holes.
Okay.
Makes
Not the density of a state at the certain K1, density of a state of overall all K1.
Again, because technically,
Okay.
if you have a single K point, you cannot define the effective mass,
Okay.
right?
I mean, yeah, I mean,
So that's why I said, like, it's really strange language here, because this is a language of the bulk materials, where you really have to include the many K points, the momentum, because again, the the electrons or carriers, holes, electrons in a bulk materials in the solid state behave as almost like a free wave, and free wave is characterized by the momentum, by the K value. So that's why this language is completely appropriate for the solid state. It's really strange to apply now this language to molecules, because the electrons in molecules, they behave as a plane wave, they behave as a standing wave, and they're really very localized actually. And it's definitely not depending on K at all, because there's no really dependence on K for the molecules, right? So, but quantum dots is kind of your artificial atoms, right? So you kind of really can go in between molecule approach and the solid approach, the bulk approach.
So please consider to make comments on the stuff and then return to the author. If if you want to suggest something.
So, but technically we expect that the denser your density of states, the higher your peaks in the density of state, should correspond to the heavier carriers, either hole or electron.
So hole has the bigger mass then, because it has higher density states. Or denser states, higher peaks compared to the electron.
But you need, of course, compare them at the specific energy range, right?
I guess if you just looked at one
Yeah, you probably,
EV interval.
yeah, I would say like you probably will be looking something near the valence band, near the edges of the valence and conduction band, near the band gap.
Yeah, at least in this, near the band edges anyway, it's heavier. Which is, well, that's what the effective mass approximation is usually for.
Okay.
Anyway, so.
What is the reason to compare this particle in the box density of states and DFT density of states? What can be learned from it?
See if reality is consistent. In one sense. I guess you can also check to see whether the wave functions behave as you expect in DFT.
So identify nature of the features in the DFT dose.
Yeah, so you can see for the particle in the box, these are
Like S and P states, right?
S and P states. So this is just like your lobe just kind of circulated around in all three directions. And then for your n equals 2 state, you get the node in the middle. You just do that across all three directions, so S and P orbitals. And if you, well, it's not very clear on this image. I could probably zoom in. But for the orbitals, you get both the features of the envelope function and the molecular orbitals. So you get the high envelope frequency. So just going back one slide. So what I was talking about is we're looking for these green waves, and then for the cone Chab orbitals, you get the green waves plus the orange stuff. And one thing that I'm trying to do in the future is just see if I can isolate the envelope functions for each part charge.
Oh, you mean for DFT part? You want to
Yes.
kind of
See
separate the envelope function for the DFT part?
Then you can get the wave function, or not the wave function, the wavelength of the envelope
But
function.
But again, comparing the orbitals, if you're not looking just on the electronic levels, not really on the dose, but comparing the orbitals, the symmetry is close to what you see or not? Because it looks like the lowest occupied and the lowest unoccupied states in both cases should have like S type of symmetry, right? During the level function.
Yes.
And again, it can be disturbed due to the presence of this block function behavior, right? But if you look on your DFT orbitals, do you think it's having this kind of shape more like S? Or more like P?
I think it's S for the near band. So does anyone remember how to zoom in on PowerPoint?
Control plus? Or control scroll up maybe?
Control plus. There
Works.
you go. So for these wave functions, they kind of the edge led atoms, so those are the exposed surface. It's kind of hard to see, but they hybridize with the oxygen P orbitals, so those are kind of like the end nodes, because you see those all around in each X, Y, and Z. So the envelope function kind of goes from oxygen to oxygen across the
So
same.
it's kind of distorted spherical shape.
Right. Yeah, because you only get it across the face, like the faces of the 1, 0, 0, or 0, 1, 0 of all the crystal faces. So it seems to take a spherical shape. The LUMO is less
Spherical.
Yeah, less spherical. There's
It might be
maybe
also.
it's-
It might be. It's also might be a signature of your some kind of maybe not really defect state, but maybe some kind of surface state, maybe because it's kind of on the left side, I mean bottom side, rather than spread over the entire system, right?
Yeah, but I've seen other people have computed orbitals for quantum dots that didn't have ligands attached to them, and some of them still have the same feature of like of the LUMO only going across 2 of the bands. So it seems to be a consistent thing that shows up in these calculations. I don't know if they use VASP or not.
But there are 2 things which you probably need to think about comparing these 2 models. So technically, this model for the particle in a box model, three-dimensional box, right? It has, what about the potential size, height?
Potential height.
Your box.
Is
So
it,
you mean-
is it
finite
finite or
box or
infinite?
infinite box?
Oh, finite box.
Or infinite?
I think you were solving
height-
for infinite box.
There are concepts of box
No.
with infinite potential. Well,
Oh, yeah, so it'd be, yeah, like basically an infinite. That's
Infinite.
what it would be like.
So it means, and what we know from quantum mechanics, can you find the wave function outside the sizes of your box if it's infinite box?
If it's infinite, no.
But
In reality, you can.
But
leak
here,
out.
and which means you expect no any kind of appearance of your electronic clouds, electronic wave function, on Ligands. If Ligands not really involved into your model,
Mhm.
right?
I
If,
guess
if your
the-
model is just the perovskite without really Ligands on the surface. But your DFT calculations, and just intuitively, of course, we expect that electronic cloud should kind of be spread, and not just be confined exactly inside the perovskite material, right?
Mhm.
So which means that in reality your box is a finite size box.
Right.
So first you probably can think about that you need to correct this solution to go to a little bit more advanced, not advanced, I would say, a little bit heavy on mathematical part, because solution for the finite box is slightly not as simple as for the infinite box. But first of all, you probably can play with the parameter of the height for your potential. Go to the finite size potential. So means not like this, but with some size, which allows you tunneling of the wave function outside the box, even if your energy is low than the potential.
Mhm. I think we kind of artificially accounted for that. We just, the edge lengths aren't the same for each side, so you get.
no, it will not fix. The suggestion was to use
Solution for the finite box
finite
solution.
depth or finite heights of the wells, and it doesn't need you immediately need to rush and do the calculations. But if you compare and see any discrepancy, you can blame absence of the finite heights of the wells.
But you can just open books and see what would be the solution for the finite box. And of course the solution will depends very strongly on your potential, you or whatever you call it, right? And the energy of the levels. Because, like if it's higher, then we actually have a classical case. If it's low, then we have this tunneling. And then your wave function will be having an exponential kind of shape, right?
Mhm.
And inside it will be kind of perturbed solution for the infinite box solution.
If I don't remember, I think it decays.
It
Most of
decays.
its value
It
from
decays
like,
exponentially
yeah, it decays
at
like-
the ages, right?
like 5 angstroms. I think it's mostly, at least for the calculations I remember. Anyway, it was like 5 angstroms. That's where most of the density is like very low outside the box.
But it probably should decay much slowly. Again,
Quicker, not slower.
comparing to the infinite box,
5 angstrom is a huge distance. We have examples of the DFT orbitals.
but if you put finite potential, right? So then your kind of shape of the wave function will be like this.
Depending on the parameter of the heights, but if
Right,
we
depends.
if you match the depth of the box to the potential of these DFT models,
Yeah.
one should get approximately the same what is seen in DFT calculations.
I agree. Yes.
Yes, and 5 angstrom is really huge distance. Typically, the tails of the wave functions are shorter.
It's one thing. The second thing is, what about symmetry? Is your box, like your actual optimized structure, is it really exactly symmetric in terms it really looks like completely symmetric cubic box with sizes A, wherever you size 5 angstrom, 5 angstrom, 5 angstrom, or whatever the size of your box.
Not exactly.
So then it means you have a perturbation due to the symmetry. So you're not really having completely symmetric box, and probably angles of this box also not exactly 90 degrees.
Mm-hmm.
Right?
That
And
would-
again, mathematically it becomes not as simple, but this is another perturbation which will be definitely changing the solutions.
That we accounted for. So L, so we do Lx, Ly, and Lz. So we set it for each dimension. So you kind of see here, if Lx, Ly, and Lz were the same, these 3 peaks would be basically the same, would be overlapping each other. But we offset them a little bit, so it gives a little bit of broadening to the density state. So
As look, it might be not exactly
structural,
90 degrees.
right.
Solution, we have some angles, will be also perturbed.
Mm-hmm.
Will be not exactly the same as in a strike box. So, and again, it's not that I'm saying, oh, solve it.
It was there were
just some ideas.
suggestions how to interpret if the models do not coincide, which possible mechanisms are responsible for discrepancy.
Mm-hmm.
So like you actually, initially, before even doing the, kind of getting this comparison, you already can say immediately that they should not be exactly the same because of these two reasons, right? So the symmetry, kind of more, less, how to say, symmetry perturbed structures comparing to the particle in a box which you consider, even if you don't have exactly same sizes of your ABC boxes, right? So like angles might be also not, like in other words, might be not exactly cubic structure or cubic box.
Mm-hmm.
And the most important is of course your potential height. So it's actually finite box rather than infinite box, which allows the shapes of your wave function to penetrate and to tunneling through the size, which means you have non-zero probability to find your electron outside the quantum dot on the ligands and maybe even on the solvent. Very small probability, like it's, yeah, whatever. And it depends on the energy which you are checking, right? So the higher the energy, if you go far away from your valence, from your edges, right? So then of course you will have increase in the tunneling probability.
Mm-hmm.
Yeah.
Elena could help me with that. He's got a script to look at, pot car amplitudes, so.
Mm-hmm.
Or not pot car,
Block
block pot.
Yeah,
You get
so
the height
this is
from
where you can take these parameters if you want, and then probably figure out how to fix your model, and maybe then you will have much better comparison, much more exact values, I would say. Like you will be in a better way to compare them directly, one against another. But even if you don't do the calculations, just kind of
Footnotes.
ideas to explain why you're not expecting that these both models should be exactly identical.
Mm-hmm. Yeah, that makes sense. And then, yeah, I'm done with this slide. And then, I guess that's about as far as I've gotten with it. And aside from the topics already discovered, the particle in the box doesn't include spin-orbit coupling, and I mean, off the top of my head, I'm not sure how you would include spin-orbit coupling for particle in the box calculation.
This was done for the spherical box, for the quantum dots. Spin-orbit couplings fine structure calculations were done by Efros in the 80s, but his shape of the box was spherical, so which actually more complicated rather than regular box. The box.
I guess I'll leave that for Efros then. Well, I guess he did already do it.
Again, your spin-orbit couplings just included into the wave function, and then you will have more, how to say, just a portion for the wave function, which will kind of get some correction to your energy splitting and solution for your particle in the box in terms of energies. That's it. I mean, again, mathematically it's not as simple to do, but it's possible. It was done.
I guess when I said I'm not sure how to do it, I meant like me physically. It's like how to do it off the top of my head or how to include it. So.
And your spin-orbit couplings, again, if we look on this band structure, right? So spin-orbit couplings for the bulk material will be differently affecting the splitting between electronic levels for different case.
Okay, yeah. They split the bands differently,
Yeah.
so they get.
So like
yeah.
like in gamma point, you will have no splitting at all, for example, right? And they will be really more deviated in the other points, or they will be kind of, you know, you might have a splitting in a gamma point as well, but the shape of your parabolas will be different for different case.
I already guess I mentioned I talked about the envelope functions for the DFT model, and then trying to figure out a way to isolate those to compare it to the particle in a box calculations. Where's the sensor for this thing? Must be up there. So that's ground state electronic structure. And then another thing that we do a lot in our group is calculate absorption spectra, so see if we can match what's been done experimentally and see if we can figure out some rules for the transitions that we do see, or try to characterize some of the absorption peaks. So these are a couple of experimental spectra for the bromide-based quantum dots, which we are modeling. So this one's from the Notre Dame group. Some of us met at ESP. They were some of the people presenting this work. Brennan, they did the JAX paper.
What's the name?
Michael Brennan. Or that was the student that was there. It was the Kuno group.
Okay.
That's
Kuno.
Kuno. Yeah, it's from the Kuno group. And then this one was from some group in Belgium. I don't think that's or Belgium. I never saw their name before. But
And the dash line is emission?
yeah, dash line is emission, black line is absorption spectra for different sizes of quantum dots.
So what again, your quantum dot size?
1.5.
So
it'd be
twice less.
yeah. So we expect more comparisons to something like this, or the bottom one over here. Although I'm not sure what size that is. But basically, you should see more blue shifting and more. But you should see more distinct peaks, like near the band edge. As you become more quantized, you should see.
Because of the S and P harmonics of an envelope function.
Yeah, they'll be more overlap, so they'll be more enhanced. And so
what is exciton Bohr radio size for these materials, where you really expect, this is a parameter which people use to say where you really should have the confinement effect being significant. Means you really can see this.
Yeah, for this one it's
splitting in levels.
7-8 nanometers, and you kind of see here. So 11, 10, 9. It shifts a little.
So it means if I go to 12, 13, and so on size, then the spectrum will be not really shifting and changes after that, right?
Right.
After 12 nanometers, I expect no really significant changes to the spectra should be noticed, either in energy or in the shape.
Yeah, they should all be emitting around 510, 520 for anything above like 10 nanometers. Yeah, so just to continue our particle in the box modeling, we tried to see if it would be possible to model spectra just from a simple model from particle in a box. So the first initial thought that we thought of was using the energy density state. So basically what that is if you just consider a transition and then just count, like bin that into a histogram. So you just account for all possible transitions and that they're all equally likely within a certain energy range. And you just plot them and give them a little broadening for spectra, and that's what this chart is here. So this energy here would be like the HOMO-LUMO transition.
So here you're not really looking on the transition density values, right?
Right, this is just looking at
bright or dark, it's all possible excitons
all
which you can make.
Within a certain energy range. So here would be from 3 to 4 nanometers.
But it's interesting that you already have this kind of shape structure and some kind of features, right? Even if you're not applying the the selection rules, right? Which kind of will be probably making it even more shapy.
Structurized.
Structurized, yeah.
So the source of these features are quantization.
Between levels.
Yeah, so you can see this transition here is from basically the lowest hole in electron state, so your n equals 1.
So you need, how many quantum numbers do you need to identify a single transition?
So 6 for each transition for this model. So in the second layer transitions, that would be
quantum numbers? So 3 for electron, 3 for hole?
Right.
6.
So 3 for each
carrier.
Yes, so X, Y, Z, because that's how we set up the model.
So it is basically what you are writing here.
Yeah, so that's what these numbers represent. So this would be 112 to 111 energy, and basically just keep repeating that pattern for up to the third state, I think.
It's just
Or no, so these are just the
probably
SPP
would be
states.
interesting to compare the same information with your DFT spectra, like if you just look on all possible transitions.
And then that, well, I did do that, and it turned sideways on here.
It is because of transition between Mac and PC. So it's revenge of Microsoft.
I guess I don't know if this is what you meant by comparing. You meant DFT EDOS to particle EDOS?
Uh-huh.
So I guess this is comparing DFT Spectra with DFT EDOS.
And
Oh, if
which
the
one
lines
is-
are transparent, you can align them and show them.
Ah, yeah. So like this top guy, I mean the insert, this is the real Spectra, including the selection rules, including the transition.
From
dipole
DFT,
moments.
yes.
Mhm.
So that's the red curve, and then the
And on a, you put it on a top of the just all possible transitions, right?
yes. So it's just counting all possible transitions from.
And for your all possible transitions, you already don't have such a discrete spectra as it was for the particle in the box, right?
Right. So you see the lowest transition only has like only a couple of counts, and then the higher in energy you go, the more states that you have. So it basically,
But interestingly, these peaks, would they, like those peaks after you really kind of calculate the transition dipoles, right? Do they correlate with those features in your all possible states from particle in the box?
you're talking about my red curve with this one?
Versus this one, because looks like you also have peaks which probably, again, energies might be different because we know you're not getting exactly the same energies. But the splitting between these states probably is comparable to what you see in your particle in the box. Maybe.
Yeah, I think. I guess I was in a rush when I put this together, so I didn't put it on here. But you could see, well, just comparing this image to this image, you see 1, 2, 3 peaks and within 1 EV, and then I guess this is.
A little bit less, two and a half maybe.
But you still see many of the same features show up. And so, and another thing I noticed is this plot on the right is basically the oscillator strength versus transition energy for the DFT calculations.
Does this feeding takes care of all transitions or only brightest ones? It looks like very repeatable trend. They all go into on a line.
Yeah, so this is a log plot. So basically this here is like the lowest energy on the LUMO. And then the higher the energy you go, the oscillator strength decreases pretty exponentially.
So your y-axis is your the energy of excitation, right?
Y is oscillator strength on a
Y
log
is
scale.
and x is your energy difference, the energy of the exciton, right?
Yes. And so that's how this purple figure turns into this red one. So the higher in energy you go, your transition probability becomes exponentially less. So but you have a lot more transitions. So your features are more resolved with each other than compared with EDOS.
Interesting.
So yeah, I thought that was just an interesting thing because I think EDOS is pretty comparable to like a bulk absorption, because since you have such finely spaced energy states, a lot of them overlap with each other. So most transitions are equally probable in a rough sense. But when you go to confinement, that trend decreases. Your lowest energy ones become higher, and your higher energy transitions become much less likely. And I think I just have one more slide on this top.
Instead of feeding, we can all just turn
Pause.
on.
Just tell us what is the main point for showing this slide, for comparing these features.
So this was just the DFT computed transitions. So, and then basically the question marks were atop each feature, like where they arise from.
Here's your spin orbit coupling now.
Yes, so spin orbit spectra. And it's basically what I did. Oh, Jesus.
So you can avoid it in the future by I don't know how.
This is really
guess
strange. Usually it's not converted
copy
to slides.
copy pasting images as bitmap.
Or just putting it in PDF format. If you don't have any features for PowerPoint, you can use PDF format for slide presentation.
I guess it probably take too much time to rearrange it. So basically, it's just a plot.
But
of
we do have printouts with kind of sketch of.
It's just partial density states, and it marks each like prominent feature or each
Mhm.
peak in the density states,
Mm-hmm.
and then you can assign possible transitions from valence to conduction band. And then that would be a way to try to identify bright transitions and less bright transitions, and characterize the how the spectra is generated that way.
Mm-hmm. And what is the main message from this assigning of transitions to specific features?
So you could determine possible selection rules, or possibly
Which rules?
possible selection rules for transitions. Aren't there molecular?
What is
Selection
this
rules? I don't know yet. I haven't
What rules?
for optical transitions.
What kind of rule is it?
You're not telling that you found the selection rules.
Right.
You're
It's
posing
something to identify.
a
That
goal
could go in
that-
the paper.
This analysis may help you to identify possible selection rules.
Yeah. So between like states that are heavy. in-
John is saying is Laporte selection rules. Or
Which?
Laporte, I don't know.
Yeah, those would be-
symmetry allowed transitions.
Well-
yeah, that'd be something to try to identify.
For the solution, for the spherical solution, where the solution of your wave functions just giving you pretty much similar to what you see in a hydrogen atom solution, right? Due to the spherical symmetry. So you get in a Bessel functions, which having this SP and so on shapes. And then selection rules will give you just SS transition, so means you will have bright transition only between SS, PP, DD. You will have dark transitions from S to P or from D to P.
Right.
So you kind of trying to
Try to identify those features.
to
whether-
get kind of the same ideas, right? So like if you identifying your orbitals in whatever shape you were showing from your slide with particle in the box, you want to kind of, based on the symmetry of these orbitals, you want to figure out what would be the selection rule.
Yes, because a lot of people spend time identifying like atomic configurations of the orbitals, but nobody's, from what I've seen, has looked at
Envelope.
envelope functions or what possible transitions correspond to the optical spectra. So I figure that's a powerful tool we have, so might as well try and use
And
it.
could you, like you said, maybe not you said, but there was talk in a ESP conference, right, by EFRAS, who was already applying this effective mass approximation to the perovskite quantum dots, right?
Mhm.
You remember this? I don't know whether he was already published, but because he was already reporting earlier than you, at least 1 month earlier, they probably already at least submitted the paper and it should be here.
That one's already out.
Okay, good. So then, can you just remind us what how your work on this part is different from what he was doing, or he has done already?
Well, his is more theoretical, so he uses. Well, I guess he uses like, more theoretical models to generate. So he uses like Kane.
This probably is a disadvantage to your approach. If you say, "Oh, I'm less theoretical."
Well, I guess we don't.
Because in other words,
Like,
like,
Tell
I'm
about yourself
working-
in more favorable way.
I'm more like a reviewer, right? So let's say I'm getting your paper as a reviewer, and then I'm seeing the paper of EFRAS, which I didn't read. I just can read the title and look on the figures, and there would be a lot of kind of similar main ideas. Then the question is, what's the reason to publish this work if pretty much the same things have been already addressed? And if you say because it's more theoretical, then it means it's more addressed more on a rigorous level rather than you are trying to address in it, right? So this is not the way to fight with reviewers.
No, I know. I got the answer for you now. So I guess in his model, you only considered like homo-lumo transitions, and he's looking at luminescence mostly properties. So it was only a 4-state model basically. While
Okay.
DFT, it's as many states.
So they consider just really a few transitions. You extend it to much larger. But do they also have ligands? The same ligands as you have on your system, or they have different ligands?
I guess for their computations, I don't know what their model.
Do they theory take any account of ligands?
No. They account for crystal structure. Yes.
So you are providing atomistic insight of the role of ligand,
Yeah.
which is missed in.
So you can now again, if you want to really put, from my point of view, this is really probably can be as a separate paper rather than the paper where you put all these four things together. But here, your main point is not that, oh, I applied this effective mass approximation and I want to analyze selection rules or kind of to obtain the selection rules. The main point is really to kind of compare the DFT calculations, which allows you to include in an atomic level, in a more realistic level, to include the surface effects, ligands, interaction with ligands, right? Kind of all changes in symmetry, because it's not really a completely ideal box. Comparing to a very simple model, which is of course very attractive to experimentalists. The simple means you can solve, like everyone can solve it very easily and get some kind of ideas based on the theory without really doing all these calculations. So your goal is really to compare and show the role of ligands, that looks like they're probably really important. You cannot just neglect them. And again, this means that this simple model might be really losing some important things if ligands are not involved in this effective mass approximation. And again, it's not so easy to get like effective mass approximation really, I would say almost impossible. Like it's completely impossible to get ligands there on the same level as DFT allows you to do, right? And one way how you can play and thinking that you kind of have ligands is playing with the potential height, right? Because your ligands is providing this not infinitely large box, but finite size box, and the size of your potential, the height of your potential, can be kind of scaled or parameterized based on the presence of, and this is what exactly you will do based on DFT, on the presence of ligands, right? At least you can take account ligands on the level of this potential height. And then again, the question is how much this correction is really helping, or maybe even with this correction, your results will be still very, very different from your DFT calculations.
That makes sense. That might be relevant in a couple of slides, because I do.
But again,
different ligands.
And I would suggest really go very, very carefully, because he's your competitor. I mean, this paper, not he, but the paper.
Right.
Against this paper, you're like, it's very easy for reviewers if they are in the field and they know about this other paper, right? So because it sounds very similar, they immediately will ask, so what exactly new? And if you're not really clearly represented in your text, right? And again, in figures, in text, in them as a big idea, so they will kill your paper right away.
Oh yeah, that's helpful.
So again, it's not really finding selection rules or something. I would say it's really trying to focus on a role of surface, and specifically surface ligands, on these selection rules, and comparing the simple model versus atomistic level model from DFT.
Yeah, that makes sense. So, yeah, I guess we already talked about those. And then,
What were they?
Oscillator strengths of the PDOS images from like one peak to another peak. So just identifying those oscillator strengths, seeing which ones are bright, which ones are dark, and then identifying certain reasons, whether they're ligands or whatever other atomistic reason for those rules or for those trends. And then also maybe selection rules for particle in a box, because this is from a paper from Dimitri from a while ago, and then they did some modeling where they approximated their thin film. That's what the model was.
Is Dmitry?
This Dimitri. The Dimitri. So they're doing with a thin film, so they considered one dimension as an envelope function, and then did some calculations of the transition dipole from the associated wave functions and found some trends, but I don't know if that would be worth exploring for our system, because it seems, well, we have another 2 dimensions we have to quantize.
But then you just repeat the same equation for each
3
dimension.
times, yeah. Very simple.
Yeah, I guess because this is X,
And
Y,
cross.
Z, and not radial.
And cross as well, right?
Yeah,
With
so-
different,
So
different X
you
and
could
Y.
apply this equation for making not the
You just need another sum. to
EDOS but actual absorption
Mhm.
spectrum based on particle in the box.
You just
You
will
do-
have additional sums with respect to x, y, and z n values, like your quantum numbers values, right? So it means you
Just copy and paste this 2 times with some different.
three times,
some to see.
three directions, right? Each.
Well, this is for one direction,
Well, yeah,
so then another 2.
but
That's
you
split
will
out.
have sum over all three directions, right? Will
Mhm.
be
Right.
inside each direction, and also cross terms also might be possible, like and from E and X to E and Y, right? E electron and X to the E whole and Y. This cross terms also probably might give you not zero oscillator strengths.
Start with 3 and then go up from there. If it doesn't look nice. So, yeah, possible future work for absorption spectra. So then, structure to property relations for ligands. So this is just kind of an overview of something I'm doing for the hobby group, for some things that I include for that paper. So, density states are turned sideways. But basically we're comparing like a fully passivated quantum dot, remove one ligand, see the absorption or the band structure, and then compare that to a replaced ligand. So this one is the fully passivated dot, and as if you look up and down, this is like a healthy band structure or healthy density state structure. So there's no trap states on the inside of these. And you can see the orbitals; they look pretty healthy for the most part. This one looks a little funny, but you can ignore that for later.
But you don't have charge density away from the core.
Right.
They're
So it's all
on
inside.
perovskite.
Yeah, so it's all inside, so it's...
Aaron, before you go forward, can you quickly remind us about the charge balancing? Are your models charge neutral, or you artificially charge them, and how
It's
does
neutral
it?
because it's balanced by ligands, right? Positively charged and negatively charged ligands.
It's...
Or is
We minimize it as much as we could, so it's a +2 overall charge.
Oh,
so
it's
so this one
in
is,
the charge.
yeah, so it has a +2 charge.
What would happen to the DOS if you do not do this +2? How DOS would change?
Means
So
you
if
take
you-
the same system and not put in the charge.
Right. So if you just let DFT calculate it or count for all the electrons, you just get a couple, like these bands would be filled.
Okay,
Couple.
so it will be like red field area in the bottom of the conduction band.
Which
Yeah,
means
it'd
you
be-
will have no really band gap problems.
Yeah, so it'd be like p-doped, like what
Okay.
Danielle's been talking about previously. And
But why actually 2 plus? Like, is it possible to really get rid of this 2 plus by the ligands to balance it completely to neutral system? Is
you
it
could
dealing
get-
with like it's really because of the symmetry? I don't know, size. If you make it larger, then you probably can really make it neutral, or
Then you need to add or remove ligands, and then it will lose the symmetry. Then
Yeah, so it's-
one side will be more preferred than another one. You cannot remove 2 ligands.
So-
Because of yes.
like, I was just what he was saying basically. So if you remove any of the ligands, you'll have an asymmetry of ligand distribution on one side. So with the +2, you have
but
the
they
same number
might
of
like
ligands.
again. You take one ligand, your charge becoming 0, neutral, right? So of course the geometry will be changed, and the ligand, even if you take in a ligand from some of lead or whatever sides, right? So the other guys, the neighbors, might be kind of redistribute themselves to kind of minimize this loss of a ligand, and maybe reorganization happens in a way that
Each
you
of
will
them,
be not really seen a very distinct side without ligand.
it is expected that we will see. Well, it is interesting to explore, but
But you haven't.
each surface lead transition metal ion needs to be coordinated to experience correct octahedral coordination.
But my
If you
question is-
remove one ligand, it immediately will create. It's not only the total charge; it will create under-coordinated metal ion that will experience different crystal field splitting, and the
But then you
electronic
can
structure
take
will
one lead
it will
out,
be-
or one what? No?
the gap will close immediately. Structure will be screwed up substantially.
But you have played with it, like you have tried different configurations to see, like this knowledge is really coming from your how say practical knowledge on playing with this Ligands and looking on the electronic levels.
The electronic levels I've looked at, but I haven't looked too closely at like nuclear reorganization. I just account for the energies, but I don't look at the structure. I haven't looked at them in detail very much yet. So.
But in experiments, like you do in experiments, can you detect whether your quantum dots are charged or not? Is it is it really reasonable to assume that they have a charge?
If you could isolate the defects, it would be possible. So I think I was just looking at one paper recently. They used ion coupled spectroscopy, and they could find defects that way. By defects, do you mean like lead defects or ligand defects?
No, not defects. I'm saying like in your case, you don't have any defects right now, right? Right. You have, but you have 2+ charge.
Yes.
So my question is, can you detect experimentally whether your system is neutral or charged?
There are sophisticated ways to do it, but we don't have access to those in the hobby lab. So and you have to isolate the defects.
You can't do it.
Right.
But have other people tried at least?
Not for perovskites. I saw they did one paper for cat selenide, but you have to find a way to isolate the defected quantum dots from like the whole ensemble, which is an idea I've been actually trying to play
So in
with.
other words, no one really knows whether the system's really charged or not charged.
But they do know, like based on size, like the stoichiometry. And for smaller particles, it's lead heavy, or lead bromine. So this is the right
lead
surface.
Enhanced. You have more lead?
Yeah, so it's the structure, so we have exposed lead and bromine instead of the other possible surface termination.
So it is what Daniel is doing, right?
Yeah, he was terminated differently.
Exposing different surfaces, lead rich or cesium rich.
Yeah.
If you have a surface like this, you would need the ligands to cap it. So yeah, so 2+ full passivation ligands. And what I did is, I removed one of the anion ligands from the lead, so it's kind of hard to see, but you can kind of see it from the orbital. Normally there'd be an acetic ion here, but I removed it. You can see that the p orbitals of the lead is exposed, so it's like a shallow surface state. If you look at the density of states for spin restricted, you can kind of see it at the band edge. It sticks out a little bit past 0, where compared to...
Oh, and just again, go back to your charge question. So when you remove one anion ligand, it means you still having a +1 charge, right? It was +2 before, now taking one, and your anion ligand has -1 charge.
Yeah, so now it's +1. So I change the charge whenever I...
So anytime you play with ligands, you automatically adjust charge to
By
have
one.
the gap opened and avoid effect of p-doping or n-doping.
Yes.
Okay.
Because I would assume that if the ligand leaves, it's going to take its charge with
So
it.
probably your thinking was that if on experiment there is a distribution of differently charged or differently ligated dots, only those that have correct stoichiometry of ligands and charges would flash light, and others will stay dark and you will not notice their signals.
Not in those words, but yes.
Okay.
It would have an open gap. That's as far as I went. But
And I have a question to John. I don't know, we discussed that you kind of noticed about the charge on this quantum dot with a dye from Peng, that there were some kind of issues that he didn't really probably assign the charge correctly. Have you already looked, like did you try to play with the charge and see whether your density of states really very affected and you see this appearance or disappearance of states inside the gap due to the having minus charge or not having minus charge?
Yeah, so I actually have, oh, can you?
Show by sign language.
He said yes, you know.
If it is yes or no, it is enough. If you need to have longer discussion, it is...
Yes means if you make it neutral instead, like if it's supposed to be negatively charged, if it's supposed to be negatively charged, but you make it neutral, then the band gap is closing and we have pretty much the same story as Erin was discussed with his charges. Yes?
You can tell now something.
Now we can hear you.
Oh, you can hear me? Okay. So yes, I played around with some of the charging, and at a certain point, the gap actually opens back up with the quantum dot. So instead of having, partial occupations right next to some type of unoccupied, you have an open gap with just a very partial, like non-filled orbital right at the edge of the valence band.
Okay, so then it's very similar to what was discussed with this perovskite business, right?
Mm-hmm.
Looks like if we really charge in the system, either kind of putting the negatively charged ligand but putting it to zero means not really assigning the correct charge, then we immediately see this kind of PN type of PN doping states inside the gap, right?
Mm-hmm. Yep.
Okay, good, thank you.
Okay, John, you will go off sound line.
So yes, so when I remove the anion ligand to expose a lead surface, it seems there's a shallow trap state that kind of pops out, but I would need a partial density states to totally confirm that. It could just be Fermi leveling or redistribution of charges, moving states around. And I was planning on doing absorption spectra for these two to see what the effect is on the spectra.
Can you quickly remind us what is the chemical composition? Just show which groups, which ions. Some of attendees of the room were asking other cesium ions and where they are.
Cesium would be hiding behind this ligand here. So if you look straight forward.
But your orbitals not really sitting on the cesium. They mainly
Right.
coming from lead and bromine, right?
Yes, near the band edge.
Yeah, near the whole
Yeah, so bromine, or not bromine, cesium. They're at the center of the cages, or the unit cells.
Mm-hmm.
And then the pink, if you can resolve them, are the bromines. And then, like these little gray features, those are the lead. And those are at the corners and along the face of the quantum dot.
Okay.
And then, yeah, these are just the ligands binding to the lead states. And so one thing we did, I did do with the hobby group is we followed a reported procedure from Jack's paper. So they basically just took some thiocyanate salts, so like sodium thiocyanate or potassium thiocyanate, and they just put it in the parent solution of the perovskite, and after about 20 minutes they saw pretty much near unity photoluminescence. So that kind of indicated that that those ligands were enhancing the features of the perovskite quantum dot somehow. Either they were covering surface trap states, or I think in their paper they didn't see any spectral characterizations from IR of like these lead sulfur bonds on the surface. So they hypothesized that the ligands like removed any excess leads somehow, which I don't know, that didn't really make sense to me. But so it's kind of unknown how this ligand attaches to the surface, or how it, or what its role is on perovskite quantum dot surfaces. It's been relatively unexplored. So this is something I was going to throw in for the work we've been doing there. And you can kind of see, so it binds, so the sulfur binds to the positive lead ion because the sulfur has the negative charge on it. And it kind of binds in kind of like 20 degrees.
Mm-hmm.
Like if this was your 0, so about 20 degrees. And it has some, it seems like it's doing some sort of hydrogen bonding interacting with the ligands, with the amine ligands anyway. So just some preliminary orbitals from these. So from the density states, you don't see any obvious trap states. Again, I would have to look at PDOS to see what exactly they are, but at the HOMO, you can kind of see something see an interesting feature. So it seems like the ligand actually hybridizes with it, and then the orbitals stick out with the ligand. So it's kind of like a conductive type. So
And again, you took out the ligand or what?
Or replaced Ligand exchange.
What you
So,
have done
so
again?
ligand exchange. So,
Oh, just one ligand was changed,
so
right?
here we removed one of these
Carboxyl.
carboxylic anions.
To
which was-
isocyanides.
then I just,
But it's each of them removed, or just single ligand was changed.
just a single one.
Okay.
So I tried to make the rest of it transparent, and then this one bold to stand out. It's probably not obvious, but so this is the region where the ligand binds to the lead surface. And if you look at the PDOS, you can see that the ligand hybridizes with the HOMO orbitals and actually draws some electron density towards the surface. Because normally before, all the electron density would be on the inside, but it kind of brings some to that side as well and pulls it away from the other side. So it seems to have a passivating effect, but also some sort of dipole effect too on the surface. And in the paper that we were following, they noted they saw a consistent, like, I guess it'd be 5 nanometer blue shift in their spectra. And I guess-
If they switching, if they substitute the ligands.
Yeah, after they do the treatment. And I guess just from the density states, like I haven't done the calculation yet, but it doesn't seem like it changed that drastically. So
But because you have only a single ligand,
yeah,
if you change all carboxylate groups to the isocyanate, you probably will see much more significant change.
I think in that period they noted there was like a saturation point. So they'd see like a certain amount of ligands attach, and then after like the initial 20 minutes, there would be no more like passivation. So it seemed to be limited by some sort of either surface states or some sort of equilibrium within the solution.
Concentrations.
Yes. So, yeah, so just some preliminary work from that group, but then also future possible work. There's all sorts of other possible ligand possibilities for these systems, I guess. Silver complexes have been used in like cat selenide, so it was a natural selection to try those as passivating perovskite quantum dots, and then other groups have attached either like whole transfer, electron transfer ligands to the surface, so those could be possible, or just ideas like those that we can work with the hobby group to have experimental and computational insight into passivating and improving photoluminescence properties of these quantum dots. And then the last section, excited state dynamics. And what time is it even?
You have generous 13 minutes
30 minutes.
for 25%
I would
of your
say you
topic.
have 10 minutes.
Sure.
But I think
So-
the last part we probably have seen already when you
Well,
were
well, it is
on the
imp-
poster, right?
uh,
No, we understand it's the most important part.
and it is important to practice to verbalize it right now.
No, but
How logically
I
it
would
is
say
connected.
because we suppose that people here, it's not our first time hearing about the things. Hopefully, you can go really very quickly.
We can hope, because some of these are also slides we've seen before. Whereas, I know some of these are Dimitri's slides. He's presented a couple meetings ago. So, just an overview for the section. So we do excited state dynamics and spinner basis. So that's what the first slide kind of is going to show when I get to it. And then hot carrier cooling in the systems. We calculate photoluminescence quantum yields from the non-radiative and radiative rates. And then just a comment on something I've been looking at from the EFROS paper that was brought up previously about the character of the luminescence transitions in these systems. So for a lot of systems that we work with, they're closed shell. So each state is doubly or twice degenerate, doubly occupied. So Luma plus 2 to Luma plus 1 and Lumo, they're basically the same transitions that are weighted twice from the vast calculations. And then we can go into open shell configurations where you have spin polarized, so your up and down electrons can have different energies, but your transitions are only going to be between same spins. So if you have a spin alpha LUMO and it's non-radiative relaxing, it's only going to go to other alpha states. And same with beta. And then you can do the same thing with optical transitions, but you just have HOMO down here up to LUMO, both systems. And then what we included for excited state dynamics is you can go to non-collinear spin calculation. So basically, your well, in a lot of situations anyway, your LUMO alpha and LUMO beta states aren't going to change in energy that much when you include non-collinear spin. If you include spin over coupling, it'll affect them a little bit. But non-collinear spin, they're not going to change, but you can get additional pathways for transition. So you could have a LUMO +5 to LUMO +4 in a situation where you wouldn't be able to get that in a spin polarized. And so the take-home message is you just have a lot more work to do when you do non-collinear calculations. And this is basically the same slide as previously, except just showing it in a different format. So this is like a matrix format of the possible transitions. So they're all nicely color coordinated.
So how to read it?
So we have different possible transitions which are associated with these.
So it is
here.
your way to interpret triple R matrix for non-collinear case.
Yes.
Okay.
That would be one way to interpret it anyway. So your diagonal elements are always going to be 0 because that would be like you transitioning to yourself.
But this doesn't include the information on oscillator strengths of these transitions, right?
Right, this
Your
is just a
matrix.
general.
It's non-radiative.
So yeah,
This is non-radiative.
So this is non-radiative. So this would be, this would be like an RR file, and then each of these would be like a magnitude of the likelihood of the transition from LUMO +3 to LUMO and so forth. And the color codes just show what type of transition they are. So if you're a blue block, that would be spin conserving, or like alpha to alpha. A pink block would be a beta to beta, so it'd be like LUMO 4, LUMO to +2. Spin forbidden, that would be like a LUMO +3 to LUMO, or any odd indice to an even indice, basically.
What does it mean, degenerate?
Spin
The
forbidden.
yellow.
Oh, so I guess for our system, for the if you include spin orbit coupling, you always get 2 degenerate states near the band edge. So your LUMO and LUMO +1 are
This is without spin orbit.
Yes, it is
Those are the-
non-collinear spin, yet without spin orbit.
Yes. So if you wanted that transition, you'd have to include spin orbit. So then it would just become a different color block. Or we just name it differently. We would say spin orbit coupling transition or spin flip transition. And you can probably tell from this characteristic headline, this isn't my slide either, but same information that I wanted to describe. So basically what we're trying to, well, one thing we're trying to model is hot carrier cooling in the system. So this would represent an optical absorption transition from some valence band state to the conduction band. And then these little blue lines, they represent possible states in the conduction band, and this is going in time. So in time, this jumps down due to coupling with phonon interactions, or dissipating energy. So it eventually transitions to the band edge, and you can either recombine either radiatively or non-radiatively. And so this is the technical jargon of how we compute non-radiative transition rates for carrier cooling. So these V's are our non-adiabatic couplings, which we compute on the fly. So coupling at one time, later in time, then take an autocorrelation of it. If you take the Fourier transform, you can get transition rates between states due to phonon electron coupling, which is diagrammed here in this Brett field tensor. So this axis and this axis represent orbital states, and then the z-axis, or the tall axis, represents rates of transitions. So the higher the peak, the faster the rate goes. And some interesting features for this state is so yes, it's generally known for systems of this crystal structure that the conduction and valence band edge are going to be twice degenerate in energy. So we see this oscillating feature going high, low, high, low, high, low. So these high features would be transitions between states of the same energy, or degenerate states. And then these off-diagonal elements, which are lower in intensity, represent cooling to the band edge, or rates of transitions from HOMO minus X to HOMO minus Y, or so forth.
So which of these transitions would correspond to yellow degenerate transitions on your diagram a couple of slides ago?
Oh, that'd be these.
Okay.
The top peaks would be the degenerate
Okay.
features. And then any states that are like one apart from each other would be like a spin flip transition, and two apart would be like a spin conserving transition. Oh, just a question: would it be possible to encode those into the tensor, or would it be too like to code in like the specific types of transitions, like by color, kind of like how you outlined in the matrix?
Possibly.
Might get a little too, or might be too much for one slide, but anyway, just an idea I had. And so, yeah, these represent rates of transitions between orbitals due to non-radiative or electron-photon coupling in the systems. And so to use these red field tensors, we start off with an initial condition, which we choose based on oscillator strengths or most probable excitations in the system, or ones we think are interesting anyway for initial conditions. So here we start out with LUMO plus 9, or HOMO minus 9 to LUMO plus 10, where in these figures the green represents like a reference energy density. So basically no change in energy in time. These yellow line represents changes in electron density, or occupations in time, and these blue represent increases in hole density in time, and then the dashed lines just represent energy expectation values. And this is on a log time, so -3 would be 1 femtosecond, and then 0 would be 1 picosecond. You can extrapolate the time scale that way. And so for these systems, we see that the hot carrier cooling occurs in the sub-picosecond range, so above 100 femtoseconds, but below 1 picosecond, basically. And so these are the computer rates that we have, and if you turn those into timescales, I think this is like 120 picoseconds, and this is like 250 picoseconds. 1/4, right?
Mm-hmm.
So it'd be 0.2 picosecond, or 200 femtoseconds. That's what I meant to say, not picoseconds, femtoseconds. And so, I didn't put them on this slide, but experimentally they see, or the reports I've seen anyway, is that hot carrier cooling usually occurs, it's on sub-picosecond timescales, but it's more in the range of like 500, 400, 500 femtoseconds. And variations in that could just be due to our model size. Since it's smaller, we have more ligand interactions than what you'd see experimentally. And yeah, I'm just not sure.
Because the different surface to volume ratio in the small models, the whole model is almost a surface, and therefore effect of ligands is stronger, and it facilitates
More
quicker
pumping
relaxation.
energy. Yeah, there's more electron density than what would physically be there on the surface.
Okay.
But we're on the right time scale, which is usually a good sign for models of these sizes. And so these are images of energy relaxation. The previous slide showed energy relaxation in time, and this figure shows spatial relaxation of hot carriers in time. So these line represents isosurfaces projected as a 2D slice of the perovskite quantum dot. And then orange represents a gain in electron density, and blue represents gain in hole density, similar to the previous model. And I don't know, it's kind of cool to see, so I'm just going to run it. And one other idea I had, so for the counters on here, it would be possible to include a magnetization readout, right? That would be something handy to know. So as you can see, as the electron relaxes to the band edge, the p states become more occupied, so that's what these orbitals are. So this is like a p state for the lead atoms, and then these must be p states for the bromine atom, which is behind the lead atom.
So the only correct atom is the center one, because it is the one with bulk part.
Yeah. Or it's the most easily to visualize anyway. And so along our excited state trajectory, it's we can compute the photoluminescence of this material if we just consider the oscillator strength of transitions while the electron and hole are at a certain occupied state in time. So this figure here would be like a time resolved photoluminescence. So you can see very early in the trajectory there's low energy heat dissipation that competes with non-radiative relaxation. So it's just basically like IR heat it's giving off. And then once it fully relaxes to the band edge, you see that it gives a very bright, intense PL. So the scale is off this year. I think the counts is up towards like 10 to the 6th reference. And I guess that doesn't really make sense by itself. You need something to reference it to, but we'll work on that in the future. And just to go along with this, we have our radiative relaxation rates and we have our non-radiative relaxation rates. So we compute a photoluminescence quantum yield of this system just using the conventional Kr divided by Kr plus Knr relaxation. So from the red field tensor, the non-radiative relaxation rate across the gap is 1.18 nanoseconds, and then the computed radiative relaxation is 2.35 nanoseconds. So they're roughly on the same time scale. And if you do the calculations, you get a photoluminescence quantum yield of around 33%, which is, well, generally low for these systems. It would be good for pretty much anything else, but usually if you have a fully passivated quantum value, you'd expect near unity photoluminescence from these systems when it's not blinking and other stuff, but that's a different topic. So comparing this to experiments, from what I remember, for room temperature measurements, the lifetime is on the nanosecond time scale, usually a little above. I've seen things from like 1 to 4 nanoseconds for room temperature. If you go to like super cool conditions or like 2 Kelvin measurements, they actually go to like picosecond relaxation rates, which is like 250 picoseconds. Radiative, yeah, which is interesting in itself. But we did these calculations for room temperature, or roughly room temperature, so these correspond pretty well, I think. I can't remember the non-radiative relaxation rates, but just from the physics, they're probably a little bit high because we don't include any sort of correction for the Rashba effect, which has been a popular theory which explains why the non-radiative relaxation is suppressed in these systems. And if you're not familiar with the Rashba effect is, I'll just draw a little diagram. So basically, so from earlier, this is like what you expect for a typical band structure for any materials, but if you have spin orbit coupling with, I can't remember what the technical term is, but any sort of like crystalline defect or asymmetry within the crystal, you can get spin splitting of these bands, so it would look more something like
So is it momentum dependent spin splitting?
yeah. So it's your So normally you just have one minima for your potential, for your dispersion curve. But when you include the Rashba effect, you get two minimas, which are spin dependent. So you need some sort of phonon to assist the radiative relaxation a little bit to do the spin flip. Or do the spin conserving transition. So experimentally it's been shown under extreme conditions that there is a small Rashba effect for quantum dots. So it would slow down non-radiative relaxation just a little bit for these systems.
Can you tell that this quantum yield number is the main result of your research, or I'm not sure.
I guess we would like to say that we would like to improve the quantum yield, or improve either. I guess I don't know what I mean by the word improve, because we have a fully passivated quantum dot, so we want to improve our modeling of the system so that we can get correct yields for the system. And then this right figure on the bottom, which is something I threw in. So this is molecular dynamics photoluminescence. Ewan's presented on it a couple of times. I think John was the first one to publish on it. So basically, from your molecular dynamics trajectory, you just compute oscillator strengths in time. So if you're in your potential energy well, like as you slosh back and forth, you have a probability of emitting at a certain time. So at the tails, you have a lower probability of emitting a photon, while when you're at equilibrium distance, you have a higher probability. So it's a way to try to get line widths of PL in these systems. The green curve is experimentally, I think, I get pulled that from measurements I did in the hobby group. And then the red line is what we computed from our molecular dynamics trajectory at room temperature.
So they are really in a good agreement.
Yeah, it's they're in pretty good agreement. It's a little broad. So I think one explanation I've heard thrown around is that like the temperature on VASP or for your molecular dynamics trajectory doesn't necessarily correspond to like physical or real temperatures. I haven't looked into the paper. I think Dimitri referenced the paper.
There is Maria Fernanda Sierra from City University of New York, and she found that one needs to, like, in order to model 300 Kelvin in reality, you need to run simulations at 250 in DFT if you use, but this scaling depends on the function, so it is for PB.
But our temperature is actually defined, in best cases, probably plus minus 20 or even 30 kelvins, right? So it means you're really not having temperature of 300. You're having a temperature
absolute numbers
between 250
are
350.
It's not very helpful to compare absolute numbers. If one would check trends, how the line widths would change as function of temperature, then it may show right trends as John was doing in 2016, right?
Will those correspond to more like realistic non-adiabatic couplings? Or is
No,
that
no,
separate?
for in DPL you do not need non-adiabatic couplings. You need just sampling of the oscillator strengths on trajectory, but you can make several trajectories at different temperatures and make MDPL spectra at different temperatures and compare and see how the line width depends on temperature on one hand, and dependence on the line width on temperature from experiment on another hand.
I get that. I just didn't know if we ran our simulations at 300K, if that would overestimate non-adiabatic couplings for like room temperature. It was just a question.
I don't know.
Probably don't want to float that out for other people or reviewers to hear. And so yeah, if I guess I was going to redo this, I would try to frame the whole presentation of this topic around this photoluminescence quantum yield number, which we need radiative and non-radiative relaxation for, which is the big parts we covered previously anyway, so. And yeah, this is just something I was working on last night. So for the paper that we were talking about from EFROS, basically summary, they found that if you include the Rashba effect, you get your lowest energy transitions will be not single, they'll be triplets instead of singlets. And so
Repeat again.
So
The lowest transitions would be triplets.
if you include the Rashba effect for these perovskite quantum dots, if you just included confinement, which is this step here, your singlet is lower than your triplet. But then when, in their calculations anyway, when they included it, the singlet increased and the triplets split. I guess these
You are the
energies
only
depend
participant
just
in the
on,
conference.
like the dimensions of your bodies relative to each other. And then this energy depends on the confinement energy.
So according to efforts, the singlet and triplet excitons flip their order in energy due to Rashba effect, which is controlled by size of the quantum dot. But if in your modeling the size is not correct, this flip may not happen, and this could be responsible for lower quantum yield.
Yes, and that's what.
But when you say low quantum yield, you expect triplets being more less.
They're more bright. In the experiments that the EFROS paper did, they did like low temperature photoluminescence, and they found that the the radiative lifetime was like 250 picoseconds.
Oh, but again, they are bright because there are 3 triplets, so you have 75% instead of. I mean, singlets versus triplets, right? So you have only single state to emit, and you have 3 triple states to emit.
And then 33 times 3 will be,
Why is that true?
because Aaron has found quantum yield 33%.
Ah,
If you multiply by 3,
Then
you
you
get
get
99.
you-
Convincing argument.
That should be in the abstract title.
No, but the reason why is it bright, because not because their triplets are bright, it's because there are more triplets with the same energy.
Well, I guess I couldn't describe the technical details to you, but the way he described it is the singlet is optically passive. Or when they did the dipole, transition dipole calculations, this was basically 0 for the singlet. So it's actually the triplet states that are giving the bright photoluminescence from their calculations anyway.
What is the ground state according to Everest?
The grounds.
Singlet.
Is it the ground?
Singlet, yes. So
ground
it's,
state, so it is triplet to singlet transitions?
But again,
That's
if you
what
have
it's-
very strong spin orbit coupling,
Then spin is not
It's
a
not a
good
problem.
quantum
Right.
number. Okay.
I mean, so you will have these transitions anyway.
that's kind of what I see, because I've done some calculations where I track magnetization
Mhm.
during the cooling. Once it gets to the band edges, it's
But is it does it correlate with your results? So you have a singlet, like your alpha beta, if you're not including spin orbit coupling, so then your singlet transitions, your low state is dark or is optically inactive.
or it's so for the spin restricted calculations.
Because you can look on your triplets in the spin restricted calculations, right?
Right.
And kind of
I guess the lowest
get the
excitation there
idea
was-
which of them will be like would they correspond to these conclusions, whether your singlets will have less optically active transitions comparing to triplet state, because you can just look where is your alpha and beta for creating a triplet state.
Mhm. And that'll go back to my absorption spectra slide, looking at those density of states.
And specifically
like-
just the low state, right?
Yeah, like the ones near the band edges, like the 4.
Yeah, one
The
should be
lowest?
just, let's say, alpha alpha or whatever your low state, beta beta alpha alpha without spin flip, right? And the other ones with the spin flip, which corresponds to your triplet state. Because
I see.
you construct your triplet state like this or like that or like that, so at least one of this will be already a triplet state.
I see what you're saying. So yeah, they actually, for the LUMO, there's 2. So they're twice degenerate in energy. The bands are, so there's 4 transitions for the whole LUMO.
Yes.
And then the spin flips from what I could tell, there wasn't really necessarily a trend. It's like the top two was a spin flip and a non-spin flip. The two brightest.
So you have actually both of them upright then?
Yes.
So it looks like you're not really
Yes.
in agreement with him, with his model. Which again might be because your wave functions is really perturbed, as you're showing in your first part of the talk, right?
Mm-hmm.
So we have splitting in energies is different comparing to the simple model.
Well, the discussion is partially addressed on the next slide.
And the wave
Your call will
functions
be
are also
disconnected.
not exactly the same as this model is given, which might affect, of course, the selection rules as well.
I just got kicked out.
Oh,
Don't worry, I'll bring it back. And it is like the last slide or.
So their assumption was throughout the calculations they were in the intermediate confinement range. So like,
oh, the size is also different.
yeah. So they labeled it like 16 to 5 nanometers as intermediate. So we would be more up in this confinement region. So that's where the theory would break down a little bit. And you might get, oh, who knows how the states are going to reorganize that. That was one thing I was planning on looking at. And that is the last slide. Phil will ever get there. Or I take it back, this is the last slide.
Okay, let's thank Aaron. Let's thank everyone for patience of staying longer. And if anyone is not satisfied with the discussion, there is a chance to ask Aaron more questions.
Let's go with the rule. At least each of you should ask at least one
Don't
question.
disappear, there could be more questions.
And we go from the very last row. Fatima, your turn to ask a question. At least one, right?
So my question is, you presented what you will do, or
A little bit of both. So what I've done and what I plan to do, it wasn't totally organized that way. I tried to put some slides of what I'm going to do in the future.
yeah,
So like,
nice. I think what you will do and what you already did.
yeah, so for the first couple I did it. So I described what I did for the density of states and what's missing and further work I could do. So future work for modeling the ground state structure would be trying to find the envelope functions of the DFT calculation wave functions. So that's one possible thing I'm looking to do in the future for that project. And yeah, so it's a mix of both.
So, in one of those last slides that you were talking about, you have, you basically come to the conclusion that your excited state modeling needs to have non-zero magnetization.
That's what the nature paper says.
Okay.
That's what they predicting.
I guess I just don't really understand, like, the figure in the bottom there. They have, like, the box and an inversion asymmetry direction. I don't know what that's supposed to mean, I guess.
So that's the Rashba effect. So if you have spin over coupling in your system with inversion symmetry, so it's like if you don't have a perfect cubic structure,
Yeah.
like if one of your atoms are displaced, you're going to have some sort of an internal electric field which create a magnetic field, and then couplings happen.
Yeah.
And that's the Rashba effect.
Okay.
Very non-technical language.
But to see the Rashba effect, you need to apply the magnetic field. Am I right?
Or it's an internal, it's a crystal.
Okay. You don't need to.
Right.
So, it's just
from the crystal
internal
structure.
field which is going kind of in an opposite direction to the, like what exactly reverse or invert?
So it'd be, so if you had a surface and you had a field going perpendicular to the surface,
Uh-huh.
then in that direction you'd have some sort of Rashba effect.
Ah, okay. So your internal field should be really being kind of in a special direction with respect to your surface.
So you could have it in X, Y, or Z, or some sort of combination. And I guess it's not really known in perovskites what causes it, whether it's due to surface or if it's due to like misalignments of the cesium in the middle that cause the charges. Have any ligands with them already, and then passivate them.
Well, cyanides are known as a very good ligand for many metal-organic complexes, right? So they naturally hybridized and coordinate with transition metals, including lead.
Yeah, so this
So
sulfur
this
group,
probably is the reason why they look on these ligands, because they're just very common ligands. And again, it has to be also negatively charged, right? Because it has to substitute for carboxylic groups to be attached to the
Right.
positively charged lead.
and the sulfur satisfies that. It has a negative charge on it.
Well,
So-
isocyanide also has this charge, because let's say you can use pyridine. So you were showing actually some of your slides showing the other, yeah, like these ligands, right? I guess some of them might be neutral. I don't know exactly how they. Looks like or both of them, like this right one. Looks like this probably will be neutral ligand.
John would know. I
If
think
they're not really functionalized with some negatively charged group. But technically, again, this type of ligands or molecules kind of probably well known just from coordinated inorganic chemistry. So, and the choice is just to have a ligands which can coordinate the transition metals of maybe of specific groups.
Yeah, the Paul Acevedo
chemistry
guy, he's been
point of view.
like I didn't know who he was before this paper, but I looked up his Google Scholar. He had like a research index of like 100 or something ridiculous. So I guess he's been working in this field for like 20 years, so he knows all the little tricks, things to try.
Who? Tim Leon?
Paul Acevedo
okay.
from Berkeley.
Analizados.
Satisfied?
Yes. So I guess my question would be, you talk about particle in a box versus DFT, like way in the beginning. You don't have to go back to it.
Okay.
My question would be, is there any particular reason you're looking at particle in a box? Like, would there be any advantage in modeling this as particle in a box?
Just to see if
Simplicity.
see if you can use a simple model to describe something that's a little more complex, like DFT, or see if the trends in DFT correspond to.
How long it takes you to do just optimization of your structure from DFT?
Like,
Days? Hours?
I think this one took
months?
like a month.
See?
Just 'cause of
because
the
his system
ligands.
is really huge, much bigger than anything you were working. So,
And,
like, to
what-
get
what-
all this data, it took you probably years, right?
Yeah, like
to
half a
collect
year.
all of them.
It's a process for something this size.
Yeah, and particle in the box, you were working on it less than months, right?
Yeah, well, I think.
How the size and shape of your quantum dot relates to the cubic box? What's the shape of the quantum dot?
Oh, it's naturally a cube, so it's. I guess before this, a lot of like cat selenide, which selenide works on, it's more spherical in shape. It's not a perfect sphere, but it's.
You were working on it,
Sphere.
right? Of course,
So-
you cannot call it a sphere, but you cannot call it a cube as well.
You can approximate it as a sphere. It's a spherical cow.
But his structure definitely has much more pronounced cubic symmetry.
So you can use particle in a box instead of, I guess the effective mass is designed for spheres. So
Again, effective mass is not really
For any specific shape.
affected by the size or the shape, because it's technically taken just from the bulk calculations, from the solid crystal, right? So that's why they usually take effective mass just from the bulk, and then all other parameters with your size, right, which leads to the confinement, and the block functions again coming from the bulk.
mm-hmm.
But you will see
Yeah, you'll learn
how
in
to
PCAM.
solve particle in the box problem in quantum mechanics. So undergraduate students can solve it, at least in one. No, but there is no actually sites available to put a ligand at that point, right?
Right. Are you just saying just put it in the box just to make the cell neutral?
Yes.
Oh, just a particle in the box?
No,
Or no, like
just
in,
make the
in the unit or in the vast periodic cell. Just you have your quantum dot and then just put two like, negatively charged ligands.
or
just to
maybe
make the whole cell neutral.
free floating counter ions.
Right. I guess.
Not on the surface, but away.
Right.
Somewhere.
I guess you could, but then
But
you could
this
do it
is
for
how,
ground state.
well,
But then if you're gonna
it's
do
not
it
exactly, but this is how the VASP is calculating the charge, right? So the charge is introduced as a field, kind of like to. Don't forget, in VASP you use periodic boundary conditions. This is very different from Gaussian. When people do charges in a Gaussian, it's not a problem. For VASP, it's a problem because you duplicate, right? You replicate the unit cell infinite number of times. So means you don't have 2 plus charge. You have 2 plus charge infinite times infinite times for the replicas, which means you will have not realistic results if you just add the charge. So to avoid this, what is happening, let's say you have in +2 charge, right? So it is assumed that you have a point charge, negatively charged point charge, on the edges of your cell, kind of, which is far away, taken far away from the actual system, right? And it's not really point charge, it's a field which having a source, means it's more dense charge, at the edges of your unit cell, and then it's kind of reducing, kind of exponentially decaying to coming closer and closer to the system. So you don't really have interaction between the field and the system. But your cell becomes neutral, right? Because you're kind of adding 2 minus charge, which is spread over the entire unit cell with not uniform distribution of the charge. So it's a field with not uniform distribution of the charge, which is kind of very similar to what you expect from the counter ions, right? Because your counter ions do not really interact with the system. They're not really having this electrostatic interaction, because if they do, we should see really very strong effect of this interaction, and all our models, if you're not including counter ions, will be completely wrong, right? So they not really interact directly through the electrostatic effect because they are probably very far away somewhere, right? So that's why they're not really interacting. But they create kind of a very weak field, not uniformly distributed, and rebalancing the charges, right? So that's why I would say it's already kind of a modeling of, or a simplified model of counter ion effects is already included in the VASP calculations. So I'm not sure whether you, I mean, I don't think that if you really add this negatively charged, or you can think just point charges, right? 2 negatively charged point charges to balance the charge, make neutral. I think you will not really see significant effect comparing to the charge one because of this technical issue with the VASP. How is it really doing these charge calculation things?
Is that the paper, or is that from the paper that you referenced for the reviewer that we were talking about, or is that same idea?
paper?
Okay.
Which thing?
Markov and Bain.
What's the idea?
They
Why you're not using
they
contrarians?
explain how stabilization of charge by compensation of charge in VASP to avoid the infinite Coulomb repulsion.
Yeah. But I mean, it's very valid kind of comment, but from practical point of view, I don't think you really need to worry about it.
Yeah, then when they're insolvent, it's like they don't, like in a physical system, if the quantum dots are charged, they're going to be screened by solvent a little bit too. So they could exist.
More questions? If not, let's thank Aaron once again. So please submit your. I'll take care of it. Please submit your comments to the speaker. Speakers, please do not discard these comments, but use them to improve and implement all comments in your slides for the future. And next
Friday?
time.
Friday.
I could use it. Friday, Alisa, right?
Oh yeah, Alisa. Is she
Well,
just Alisa? No one on Friday from your group?
So far, at least on them.
And next Tuesday, there is a chance to present for John and for Alisa on her research. In 2 weeks, Fatima and Daniel. In 2 weeks. So there are expectations that you'll do something with non-adiabatic couplings and dynamics.
Yeah.
It's a big challenge. And then
We also have research presentations on Friday after 2 weeks, I guess. Starting like beginning of August. There will be research presentations on Friday from Michael.
Okay, good. And in 3 weeks, we'll start drilling the posters for ACS conference. Right?
When is the ACS conference? It's like the middle of August sometime.
Middle of August, but starting from
19th.
July,
Exactly.
starting from July 31st, we will have last meeting in July and 2 first meetings in August to drill the posters. Just bring them on the big screen and quickly guide and survive the questions. Okay, thank you much for the patience and for dedication. Thank everyone. And see you on Friday.